Thanks for watching this video. Today I'm going to talk about our work BBN, which is a bilateral branch network for long-tailed visual recognition. Long-tailed distributions could be a natural property of real-world large-scale datasets. The extreme imbalance can present tremendous challenges for the image classification task, especially for the tail classes. Rebalancing strategies are proposed to solve the long-tailed visual recognition task by resampling the examples, or reweighting the losses of examples within mini-batches. So, the data distribution of training and test sets could become close. In this work, we first explore the working mechanism of rebalancing strategies. For analyzing in depth, we divide a deep classification model into two essential parts, the feature extractor and the classifier. The feature extractor and classifier are known as the backbone network and the last fully connected layer. Then, naturally, the learning process of a deep classification model can be separated into representation learning and classifier learning. Since class rebalancing strategies could boost the classification accuracy by paying more attention to the tail classes, we propose a conjecture that the way these strategies work is to promote classifier learning significantly, but might damage the representative ability of the learned deep features. In order to justify our conjecture, we design a two-stage experimental fashion to separately learn representations and classifiers. In the first stage, we train a classification network with original cross-entropy or rebalancing methods, such that we could obtain different kinds of feature extractors corresponding to these learning manners. When it comes to the second stage, we fix the parameters of the feature extractors learned in the former stage, and retrain classifiers from scratch with the aforementioned learning manners again. As shown in this figure, we conduct several contrast experiments to validate our conjecture on long-tailed cipher and iNaturalist datasets. CE cross-entropy, RW reweighting, and RS resampling are the conducted learning manners. As observed, when fixing the representation, the error rates of classifiers trained with RW or RS are reasonably lower than CE. While, when fixing the classifier, the representations trained with CE surprisingly get lower error rates than those with RW or RS. To evaluate the generalization ability for representations, we utilize models trained on Cipher 100, as the feature extractor to extract the features of Cipher 10. And then perform the classifier learning as the same as the aforementioned. It's worth noting that the experimental results still hold on iNaturalist datasets. It can be concluded that the way these strategies work is to promote classifier learning but damage the representative ability of the learned deep features, perhaps due to distorting original distributions. For exhaustively improving the recognition performance of long-tailed problems, we propose a unified bilateral branch network to take care of both representation learning and classifier learning simultaneously. As shown in this figure, our BBN model consists of two branches, the conventional learning branch and the rebalancing branch. In general, each branch performs its own duty for representation learning and classifier learning. As the name suggests, the conventional learning branch is responsible for learning universal patterns for recognition, based on the original data distribution, while the rebalancing branch coupled with a reversed sampler is designed to model the tail data. After that, the predicted outputs of these two branches are aggregated in the cumulative learning module by an adaptive trade-off parameter. Alpha is automatically generated by the adapter according to the number of training epochs. It can adjust the BBN model to firstly learn the universal features from the original distribution, and then pay attention to the tail data gradually. More importantly, alpha could further control the parameter updating of each branch. For example, it avoids damaging the learned universal features when focusing on the tail data, at the later periods of training. In experiments, empirical results on 4 benchmark long-tailed datasets show that our model obviously outperforms existing state-of-the-art methods. We also provide adequate ablation studies and analyses. On Cipher 10, the L2 norm of classifiers are visualized for different learning manners. Obviously, the L2 norm of 10 classes weights are basically equal, learned with BBN. Meanwhile, the deviation is the smallest. Besides, we visualize the compactness of features learned by different learning manners. The features learned with CE could gather more closely than those learned with other manners. It also proves that rebalancing strategies could do harm to deep features. If you want to learn more, we recommend checking out our paper. Thanks.